Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be looking at the graphs of derivatives. So because the derivative is a function, the derivative function can actually be graphed. And the graph of the derivative is actually closely related to the graph of its original function. So the graph of y equals f of x and the graph of its derivative y equals f prime of x are closely related to each other. And that relationship all stems from the relationship between the function's behavior and the slope of the tangent line. So we've seen this slide a few times now. If the function is increasing at a point, then the slope of the tangent line, or the derivative, is positive. So the derivative will take on a positive value if the original function is increasing. If the function's increasing, the derivative is positive. Now, if the function is decreasing, the slopes of the tangent lines are negative, so the derivative will take on a negative value. And up here, where the function is neither increasing nor decreasing, the slope of the tangent line is 0, and the derivative is equal to 0. So this is what is called a maximum, but this is not the only type of point where the derivative can equal 0. So this kind of just sums all of that up. Make sure that you write this down. If the derivative is positive, then f is increasing. And the same is true in reverse. If f is increasing, the derivative is positive. If the derivative is negative, then the function is decreasing, and vice versa. If the function is decreasing, then the derivative is negative. And there are a bunch of different scenarios for what the graph could look like where the derivative is equal to 0. We already saw one of them at this type of maximum right there. And you could also have a minimum. That's the same thing. So at this minimum right here, the slope of the tangent line will be 0 and the derivatives will be 0. And those are not the only two scenarios that will give you a derivative of 0. In fact, any point where a function flattens out will have a derivative of 0. So picture y equals x cubed for a moment. I'm going to try my best to draw it here. Y equals x cubed looks something like this, and right there in the middle where it flattens out, that will have a horizontal tangent line, and the derivative will be equal to 0. And, same thing, if you picture negative x cubed is going to basically do the same thing. So right there where it flattens out in the middle, we'll have a derivative equal to 0. Now, these are neither maximums nor minimums. We're going to talk more about points like this in the future. For now, we will call them saddle points. And really, any function that has a horizontal section or a horizontal line in general, anywhere where the function is constant, so whether it's the whole function or just specific intervals, any interval where the function is constant and a horizontal line will have a derivative that is equal to 0. So what we're going to do for this function here, this is a very generic f of x, so because I'm not really giving you any x or y coordinates, I'm not even giving you a function, we're only going to graph an approximation for its derivative. We're just going to draw what the behavior of the derivative's graph should look like. I'm not looking for exact coordinates here. I'm not looking for anything perfect. I am just looking for an approximation of what the graph of the derivative should look like just based on the graph of the original function. So we're going to look at the slopes of the tangent lines, and we're going to graph an approximation of its derivative in the same coordinate plane. So let's start with where the derivative would equal 0. So there is a minimum right here and a maximum right here. At both of these points, the derivative would equal 0. Now remember, we're supposed to draw the graph of the derivative. So the derivative has a value of 0. The 0 of a function is also known as an x-intercept. So right here at this minimum, the graph of the derivative is going to have an x-intercept. And at this maximum, the graph of the derivative is going to have an x-intercept. So there's going to be an x-intercept here and here. And these are the only 2 points where the derivative function is going to touch or cross the x-axis. Now, everywhere else, the derivative graph will either be above the x-axis or below the x-axis. Values that are above the x-axis will have positive y-coordinates. So the derivatives will be positive for any value that's above the x-axis. Values that are below the x-axis have negative y-coordinates, so the derivatives will have negative values below the x-axis. Where the derivative function is above and below the x-axis depends on whether the original function is increasing or decreasing. So from this arrow to this minimum right here, if you trace the graph from left to right, you will see that your finger is moving down, which means the function is decreasing. If the function is decreasing, that means the slopes of the tangent lines at all points on this interval are negative. So, because the function is decreasing on this entire interval, the derivative is negative, which means that the derivative's graph will be below the x-axis. And then at this point right here, the graph of the derivative touches the x-axis. Now, between this minimum and this maximum, if you trace the graph with your finger, the original graph is increasing. If the function is increasing, that means the derivatives are positive. So the derivative is positive for all of these points here. If the derivative is positive, that means the derivative's graph is above the x-axis. And then for every point after this maximum, if you trace the graph, the original function is decreasing. So because the original function is decreasing, that means the derivatives are all negative. That would mean that the derivative's graph is going to be below the x-axis for this entire interval. So let's draw an approximation for this derivative graph. So from this arrow to this x-coordinate right here, the derivative is going to be below the x-axis, but it does need to cross the x-axis here at this x-intercept. So that will look something like this. The derivative is below the x-axis, but it crosses the x-axis right here. Now, between these two x values, the derivative is positive. If the derivative is positive, that means the graph is above the x-axis. However, it does need to get back to the x-axis to reach this x-intercept over here. So in order to be above the x-axis but get back to the x-axis, it needs to go up and then come back down. I have no idea how high up it goes. Remember, this is an approximation. This is not an exact graph. Then, for the rest of the function, the derivative is going to be below the x-axis and be negative, so the derivative graph is going to be below the x-axis for the rest of the graph. And so the graph of the derivative, which is here in red, will look something like this. So what I want you guys to do is I want you guys to try this one, sketch the approximate graph of g prime given a very generic g of x. I do need to give myself a little more room down there. All right, so let's start with where the derivative's graph should have an x-intercept. So right here at this maximum, the derivative is going to equal 0. So right here at that maximum, the derivative's graph will have an x-intercept. And then right here at this minimum, the derivative is going to equal 0. So the derivative's graph will have an x-intercept right here. And then here at this maximum, again, the derivative is going to equal 0. So the derivative's graph will have an x-intercept right here. So these are the only 3 points where the graph of the derivative is going to touch or cross the x-axis. Everywhere else, the derivative's graph will either be above the x-axis or below the x-axis. Whether it's above or below the x-axis will depend on whether the original function is increasing or decreasing. So from this arrow all the way up to this maximum here. If you trace the graph, the function is increasing. If the function is increasing, that means the derivative is positive. If the derivative is positive, that means it is going to be above the x-axis. Then from this maximum to this minimum, the function is decreasing. If the function is decreasing, that means the derivative is negative. If the derivative is negative, that means the derivative's graph is below the x-axis. Then from this minimum to this maximum, it is increasing again, which means the derivatives are back to positive. If the derivative is positive, the derivative's graph is going to be above the x-axis. And then after this maximum, the rest of the original function is decreasing, which means the rest of the derivatives are negative, which will mean that the rest of the derivative graph will be below the x-axis. All right, so let's put that all together into the graph of a derivative. So for this first part, the derivative is going to be above the x-axis, but it does need to reach the x-axis here at -3, so it will look something like this. Then from -3 to -1, the derivatives are negative, but the derivative graph does need to get back to the x-axis here at -1. So in order to be below the x-axis but get back to the x-axis at -1, it needs to come down and then come back up. I have no idea how far down it goes. It doesn't matter. This is only an approximation anyway. Then from -1 to 1, the derivatives are back to being positive, so the derivative graph will be above the x-axis again. But in order to get back to the x-axis here at 1, it needs to go up and then come back down. Then for the rest of the graph, the derivatives are negative, and the derivative graph will be below the x-axis for the rest of the graph. So let's go ahead and try this next one. So for this next one, this is not going to be a polynomial. And remember what we covered in the last video about differentiability. Sharp points are not differentiable. So at this point here at -2 and this point here at 0, those are not maximums and minimums. These will not, I mean, they are maximums and minimums, but they will not have a derivative that equals 0. The derivative's graph will not have an x-intercept here and here. At these 2 points, the derivative does not exist, and the derivative is undefined. Now, for this one, we can actually get a little bit more accurate for this next one because we actually have a nice grid, and we actually can tell that these are lines. These are straight lines, and we can actually figure out what the slopes of those lines are just by looking at its graph. So for the graph of the original function, yes, this section is clearly decreasing. But you can tell that we're going down 1 over 1. So the slope here is actually -1. So that means the slopes of the tangent lines will all be -1 until you get to this point, -2. So because the slope of the line is constant, the slope of the line is never changing, that means the derivative will be a constant -1, until you get, just ignore this. Oh boy, I'm making a mess. Hold on, let me try erasing that. That is a nightmare. Hold on. All right, that's a little better. Anyway, the slope of the derivative will be constant until you get to this point here. But remember, the derivative does not exist at this point. But it exists for every single point that gets closer and closer to -2. It's just not defined at -2. So I'm going to indicate that with a hole. So the hole is a placeholder, meaning that the derivative is not actually defined at -2, but we can get pretty close to it. Now from -2 to 0, this is still a straight line. It's clearly increasing. So the derivative graph will be above the x-axis, but we are increasing at a constant rate. We're going up 1 over 1. So the slope is actually equal to +1 over here. So because the line has a constant slope, that means the derivatives are all going to be constant, and the derivatives are all going to be the same, +1. So from -2 to 0, the derivative is going to be a constant 1. But again, it is not defined at 0, so I'm going to just use a placeholder of a hole at 0. Then from 0 for the rest of the graph, it is still a line, so we are going down 1 over 2, down 1 over 2. So it looks like the slope here is -1/2. So because the slope of the line is constant, that means the derivatives will be constant. The derivatives will all be the same. The derivatives will all be -1/2. So at -1/2, which we'll call that right there. From here, for the rest of the graph, the derivative is a constant -1/2. So that is what the derivatives graph is going to look like. It is going to be these 3 horizontal line segments with holes there, 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 and there. All right, so that is it for the graphs of derivatives. So in the next video, we're going to finally start covering derivative rules, which are shortcuts to very quickly find the derivative of a function. And we're going to be covering derivative rules for a large portion of, for this next large portion of the course. So thank you all very much for watching, and I will see you all in the next video. Bye-bye.